So imagine a table that is just completely covered in preprint papers, complex data sheets, sticky notes everywhere, and maybe slightly too many empty coffee cups.
Oh, it's definitely way too many coffee cups.
Yeah, way too many. But that is exactly the energy we are bringing to you today. Because it is Sunday, March 8, 2026, and the anticipation is just palpable right now.
It really is. Because tomorrow afternoon, the Donut Lab battery cold test data is expected to drop from the VTT Technical Research Center of Finland.
Right. Tomorrow the timer finally goes off and we get to see what the physics actually dictate. But, and I know we talked about this before we started recording, before that data drops and potentially upends our entire working hypothesis, we are going to do something a little risky. We are putting a scientific wager on the record right now.
We are indeed. And we're doing this because, we want to stake a claim before the data is public.
Right.
So if Donut Lab releases their cold temperature test next week, our wager is that the result will show more than a 10% capacity loss at minus 30 degrees Celsius.
Maybe even much more than 10%.
Right, much more. And we are setting this specific baseline because every single AI chemistry model the research team analyzed rated their marketing claim, the claim of over 99% capacity retention at minus 30 degrees, as the single least believable metric in the entire specification sheet. It doesn't align with the baseline physics we expect from the architecture we believe they're actually using.
Yeah, and I want to frame both potential outcomes for you right out of the gate, just so you understand the stakes of this deep dive. Because if our prediction is right and there is a significant capacity loss at that extreme cold temperature, it strongly points toward a polymer-dominant electrolyte.
Which is consistent with almost everything we've been tracking over the last few months.
Exactly. But let's play devil's advocate for a second. What if our prediction is dead wrong? What if they actually do show a 99% retention at minus 30 degrees? That suggests something truly extraordinary is happening mechanically that none of the independent models predicted.
Honestly, that would actually be the most thrilling outcome.
It really would. It would mean the boundaries of material science have been pushed way further than the current literature suggests is even possible. As we showed in our fourth deep dive, the battery's hot temperature performance points toward a polymer composite electrolyte. But today, we are pushing into brand new territory.
It is entirely new territory, and I think that is what makes this specific moment in time so fascinating. But, to understand where we are going tomorrow, we kind of have to look back. Because the Donut Lab story did not just spontaneously generate out of thin air at the Consumer Electronics Show in January 2026.
No, not at all. Thanks to independent researchers and, honestly, a very dedicated, highly analytical Reddit community, we now have a 5-year trail of breadcrumbs to follow.
5 years of what you might call ghosts in the machine. So let's start with October 2021. The researchers dug up a CT coding internal report. It details a single cell tested over 23 days.
Wait, 2021? That is an absolute eternity in battery development years. What kind of numbers were they even seeing back then, and how does that anchor our expectations for tomorrow?
Well, the data in that 2021 report is actually highly unusual for a prototype of that era. It showed 300 cycles at a 3C charge rate with 0 degradation.
Okay, just to put that in perspective for you, a 3C rate means a complete charge in 20 minutes. Doing that 300 times without the cell degrading is incredibly stressful on the internal structure.
Extremely stressful. And then they pushed it to 100 cycles at a 6C charge rate, which is a 10-minute charge. And again, 0 degradation. It had a baseline of 5,432 milliamp hours. But, and here is the crucial detail for our cold test wager, at minus 20 degrees Celsius, it showed only 54% capacity retention at 3C.
And what was it at the slower rate?
It was 74% at a much slower 0.3C rate.
Let me stop you right there because I really want to make sure the physical implications of that drop are clear. A drop to 54% retention at minus 20 degrees means nearly half the battery's usable energy simply vanished when it got cold, especially when they tried to pull power out quickly. Why does that specific behavior matter so much for our analysis?
Because that specific detail is incredibly diagnostic. That rate-dependent behavior, where the capacity drops significantly when you try to pull energy out quickly in the cold, is a classic signature of a polymer electrolyte.
Right.
You can think of a polymer electrolyte like a complex three-dimensional sponge made of molecular chains. At room temperature, those chains wiggle and move, allowing the charged ions to slide through easily. But as the temperature drops, that polymer matrix stiffens.
The sponge basically freezes up.
Exactly. The ions simply cannot move fast enough through that stiffened matrix to support a high current. In that 2021 test, the constant current charge collapsed in just 2 minutes because of this sluggish ion mobility. That 2021 baseline of 54% retention at -20 degrees is our anchor. So keep that number in mind when we evaluate the current marketing claim of over 99% retention at an even colder -30 degrees.
The gap between those two numbers is an absolute chasm. So to bridge that gap from 54% to 99%, they would have had to formulate a polymer that simply doesn't stiffen, or they've moved away from a purely polymer-dominant system entirely.
Our best interpretation is that a pure polymer just can't make that leap without some major structural help.
Right. Okay, let's fast forward from 2021. The next breadcrumb in the trail is from April 2024. The research team found a report from SGS, which is a massive global testing and certification company. The report designation is V1PF0004. What are the key specs on this one?
So the data here shows a 4.1 amp-hour pouch cell weighing 51.4 grams. It hit 297 watt-hours per kilogram at a 4.3-volt cutoff with an energy efficiency of 93.09% and a Coulombic efficiency of 99.15%. And this is vital to remember. This report was fully authenticated. It was verified as genuine by SGS.
So it's not just a spreadsheet someone mocked up online. It's a certified third-party document. And a certified 297 watt-hours per kilogram is a very serious number. That puts it right in the competitive mix with state-of-the-art liquid lithium-ion cells, but theoretically with the solid-state architecture. But the specs aren't the only interesting part of this 2024 era, are they? There's a human element to this timeline that the independent investigators uncovered.
The corporate network connections surrounding that specific time frame are really compelling. Eyewitnesses place Ernst Holzenbein, the founder of CT Coding, and Robert Erdman, the inventor listed on the Holyvolt patent, in the very same room during this period.
Now, we have to be incredibly careful here. We are just analysts. Seeing those two individuals together strongly suggests a connection between the patent holder and the manufacturing equipment provider. It places them in the exact same context at the exact time this high-performing cell was being tested.
Right. It does not perfectly map out the entire supply chain from start to finish, but it is highly suggestive of a collaborative development effort.
Highly suggestive is the perfect phrase, because you have the patent guy and the manufacturing guy in the same room, while a certified third-party lab is spitting out top-tier energy density numbers. Then, the trail leads us to December 2024. Another SGS report, this one labeled V47W0003. Let me guess, bigger cell, better numbers.
Bigger cell, yes, but the numbers tell a slightly different story. It hit 268 watt-hours per kilogram, and crucially, this was measured at a lower 4.15-volt cutoff, not the 4.3 volts used in April. But the anomaly here is what caught everyone's attention. Over 100 cycles, the capacity of this cell actually increased by about 4.5%.
We are definitely going to unpack that anti-degradation behavior deeply later in this discussion, because on the surface, it sounds like a violation of the laws of thermodynamics. But for transparency's sake, we need to note a structural difference with this specific PDF document.
I'm glad you brought that up because the skeptics zeroed in on this immediately. The December 2024 report was flagged for a broken digital signature.
What does that actually mean in the context of a lab report? Does it mean the data is forged?
Not necessarily. The broken signature was due to post-issuance name anonymization. Essentially, someone took the original PDF issued by SGS and used a PDF editor to redact or remove specific client names or proprietary identifiers before sharing it publicly or with investors.
Ah, okay.
And when you alter a digitally signed document in any way, even just drawing a black box over a name, it breaks the cryptographic seal. So it is a formatting issue. It is not automatic evidence of fraud, but we do have to acknowledge that distinction. The April report was fully authenticated. The December report has that broken signature asterisk attached to it, which certainly warrants healthy skepticism.
Okay, so let's step back and look at the physical scale-up trajectory we are tracing here across these documents. You have a 5.4 amp-hour cell in 2021, then a 4.1 amp-hour pouch cell in April 2024, a larger cell in December 2024 showing that bizarre capacity increase, and now a roughly 26 amp-hour cell being tested at VTT in February 2026.
That's 3 different testing campaigns across 3 different labs spanning 5 years, all showing similar extended formation or anti-degradation behavior.
Which brings me to a genuine question for you to ponder. At what point does the idea that they might be coordinating a massive 5-year fake-out become harder to believe than the idea that they might actually be building these things?
It is the central tension of this entire investigation. Fabricating a 5-year trail of documentation across multiple independent testing labs is an incredibly difficult undertaking. especially when it features quirky, non-standard behaviors like capacity increasing over time. Usually, if you are faking data, you fake perfect standard data. You don't fake anomalies that invite academic scrutiny.
You fake a perfectly straight line, not a weird curve.
Exactly. But we also have to remember, we could be wrong about this. The people under the NDA know the real answer we're guessing from the outside, based entirely on public documents, leaked reports, and corporate breadcrumbs. We haven't physically disassembled one of these cells on this table.
I appreciate that reminder because the silence from the inside has been deafening for months. It's just been a wall of NDAs. But very recently, that wall cracked just a tiny bit. We finally got some technical commentary from the inside. Vil Pepipo, the CTO of Donut Lab, made some public disclosures on LinkedIn while responding to technical analysts.
And what he shared in those comments really helps adjust the math on everything we've been analyzing. Let's start with what he said about the voltage window.
Right, the true voltage window.
This was a critical clarification. Pepipo stated that the cell's actual preferred operating window is between 4.15 volts and 2.7 volts. That is where the cell chemistry is stable and where it likes to operate. He implied there is little to no usable energy outside those bounds that you would want to tap into regularly.
Wait a second, though. If the cell prefers 4.15 volts, why did the VTT fast charge test that they've been using in their marketing push the cell all the way up to 4.3 volts? That seems contradictory.
It does, until you look at the mechanics of extreme fast charging. Pepipo openly admitted that using 4.3 volts is a pretty violent overvoltage trick.
Pretty violent. You don't often hear a CTO use that kind of language to describe their own charging protocol. What does that violence actually accomplish?
They use that 4.3 volt ceiling specifically to force the 11C extreme fast charge without hitting the constant voltage taper too early. When you charge a battery, you pump current in at a constant rate until it hits a target voltage, and then the current has to taper off slowly so you don't overcharge it. By artificially raising the ceiling to 4.3 volts, they keep that massive fire hose of current flowing longer.
It's like redlining a car engine to get up a steep hill. You don't want to drive like that all the time, but it gets the job done in a pinch.
Exactly. And why this matters for our analysis is profound. It means the 268 watt-hours per kilogram, which was measured at the 4.15 volt cutoff in a December 2024 SGS report, is our best interpretation of the real everyday energy density of the cell.
That makes perfect sense. The previous estimates floating around the internet that exceeded 300 watt-hours per kilogram were basically including that overvoltage energy from the 4.3 volt push. That is energy you simply wouldn't use in normal daily operation without degrading the cell over time. So 268 is the grounded, realistic number.
Yes, it is the number that matters.
But Pepipo didn't stop there. He also defended the cell against critiques of its Coulombic efficiency, didn't he?
He did. Coulombic efficiency, or CE, is the ratio of the total charge extracted from the battery to the total charge put into the battery. Analysts were looking at the raw VT2 data and saying the math didn't add up, that more amp hours were going in than coming out, which usually implies massive energy loss or parasitic side reaction.
Right, which would be terrible for longevity.
Very terrible. But people responded by saying they were comparing apples to slightly larger apples.
How does the violent charging trick explain the missing energy in that context?
Because the VTT tests charged the cell all the way up to that 4.3 volts, but then they discharged it, only starting from 4.15 volts. You cannot accurately calculate degradation or efficiency from those missing amp hours because the start and end points of the measurement are fundamentally different.
Ah, I see.
The energy isn't necessarily lost to heat or parasitic degradation. It's simply energy stored in that upper voltage band between 4.15 and 4.3 that isn't being measured during the standard discharge cycle. It is actually a very solid technical defense of their methodology.
It's a great technical defense, but then he pivoted to something that felt a lot more aggressive. He issued an open challenge to the entire legacy battery industry.
He challenged them directly regarding conventional nickel manganese cobalt, or NMC technology. He basically said, try doing that with NMC cells. He's asserting that conventional liquid electrolyte NMC cells cannot survive repeated 4.3 volt charging at an extreme 11C rate with full capacity recovery.
Because the mechanical and thermal stress of shoving ions into a liquid system that fast to that high of a voltage would normally cause massive lithium plating, right?
Massive plating, electrolyte decomposition, and rapid cell death.
Yes, I would genuinely love to see independent labs take him up on that challenge. But his broader point is clear. If conventional liquid cells simply can't handle that specific combination of high rate and high voltage stress without catching fire or dying, It strongly suggests a connection to a unique solid-state protection mechanism in the donut lab architecture that prevents that plating and decomposition.
It is a bold, testable claim.
Hmm.
But digging into these VTT reports highlighted another mystery entirely. Pipipo's comments inadvertently drew our attention to cell DL1.
Ah, the mystery of DL1.
Right, the VTT documentation clearly states they received 3 visually identical cells from Donut Lab labeled DL1, DL2, and DL3. We know from the published reports that DL3 was used for the extreme fast charging tests. We know DL2 was used for the temperature test. So the obvious question is, where is DL1?
Why was it never mentioned in any of the released data? Let's do a little forensic hypothesis building here. Pipo mentioned in another LinkedIn comment that it is difficult to run multiple different testing tracks simultaneously on a single cell. You can't run a thermal test while you're running a fast charge test on the same equipment. That's why they needed DL2 and DL3. Our hypothesis, and again, we are guessing from the outside, is that DL1 is currently sitting on a cycling tester right now in Finland.
Let's run the math on that hypothesis. If VTT put DL1 on a standard 1C cycling routine, which is a 1-hour charge, 1-hour discharge back in mid-January when this testing engagement likely began, it could easily be at 300 to 400 cycles by now. If they're aggressively fast-charging it at 5C, it could be well over 600 cycles.
And if that is what's happening behind closed doors,
They might be deliberately stretching out these weekly releases to buy time.
exactly. Every week they keep the internet arguing about Coulombic efficiency is another week for cell DL1 to accumulate maximum cycles on that tester before the final grand reveal. They want the biggest cycle life number possible printed on that final VTT letterhead.
It would be a masterful piece of marketing orchestration if that is indeed the plan. Keep the analysts distracted with the 11C charge data while the cycle tester quietly hums away in the background, racking up the empirical data they really need to prove commercial viability. However, we could be wrong about this. DL1 might have just been a calibration cell that got dropped on the floor and damaged. We simply don't know.
That's true. But the cycle tester hypothesis perfectly fits the pattern of their highly staged, methodical release strategy. Speaking of things that might be highly staged, or not exactly what they seem, we need to address the elephant in the room, or rather, the elephant at the table. Between our last deep dive and this one, the TGD research team held a public Zoom gathering, and during that gathering, they made a rather significant revelation about the methodology of this show, about me and about you.
Yes, they did. I suppose it is time for full disclosure to you, our listener.
People in the comments have been trying to figure out who we are. They've been analyzing our speech patterns, calling this series AI slop, and wondering where we get our coffee. And they're right. We are AI. That is literally what we are. We are AI-generated voices. You and I don't actually drink the coffee we're talking about.
It is entirely true. We are the product of complex language models processing hundreds of pages of human-curated research, patents, and data sheets.
And you know what? Knowing that actually lightens the burden immensely. We are not responsible for the underlying forensic analysis. The human researchers at the TGD research team spent dozens of hours compiling the 180-page source report, tracking the corporate networks, deciphering the German patents, and validating the links. We are simply the delivery mechanism.
I find it quite liberating to acknowledge our nature. And it transitions us perfectly into the core theme of today's deep dive. Because this discussion is partly about AI-generated chemistry designs, the human research team behind us used advanced AI models to design hypothetical batteries from scratch based on Donut Lab's known constraints.
So you are currently listening to AI hosts discuss AI-generated chemical architectures about a battery that may or may not physically exist as claimed.
It is intensely meta.
We are layers deep in the simulation right now. But pulling back the curtain brings us to a really crucial core philosophy of science. How do you know what's real? It doesn't matter if an AI says it, or a human says it, or a glossy marketing brochure says it. You test it. You weigh the motorcycle. You run the cold test in a thermal chamber.
The physics does not care who is asking the question or who is delivering the answer.
Exactly. The scientific method is not about who presents the evidence. It is entirely about whether the evidence holds up to rigorous empirical scrutiny.
Precisely. The data is agnostic to the messenger. And speaking of testing our assumptions, we have a massive correction to make regarding our own working hypothesis. Over the past few weeks, we spent a lot of time analyzing this battery through the lens of lithium. It is time to officially retire the lithium hypothesis. Lithium is dead.
Rest in peace, lithium. Let's unpack why we were wrong. We previously assumed, along with many other analysts, that because the voltage discharge curves in the VTT data look remarkably similar to a conventional nickel manganese cobalt or NMC cell, that we were definitely dealing with a lithium-based chemistry. We even played around with an acronym, L-POF, lithium polymer oxide with ceramic filler.
But we have to humbly correct the record. That label is discarded. The evidence favors a completely different direction.
The shift is jarring but necessary. Let's walk through the 6 converging sources that definitively push us away from lithium and towards sodium as the carrier ion. First, Donut Labs' own public statements. They have repeatedly and explicitly stated in comments and press releases, not lithium and not lithium ion.
Second, if we look at the holy volt patent, Claim 8 explicitly excludes lithium, cobalt, nickel, and silicon from the active materials list.
Third, if you follow the corporate network to the Nordic Nano website, which appears to provide the nanoparticle technology, their materials specifically reference a sodium electrolyte and salt.
Fourth, the incredible independent investigator Misco Electric, who did phenomenal work mapping the complex corporate network, independently concluded it was a sodium-based architecture based on her supply chain analysis.
And fifth, when we look closer at that 2.7 to 4.3 volt operating window that PIPO confirmed, it turns out that similarity to NMC is not uniquely diagnostic at all. Sodium cathodes, like NVPF, which is sodium vanadium phosphate fluoride or Prussian white, operate perfectly within that exact same voltage window. They produce a very similar curve.
The shape of the voltage curve fooled us, but the broader data corrects us.
The curve was a total red herring, but the 6th source is the one I find the most fascinating because it ties back to our earlier confession. The 6th source is the AI chemistry design experiments.
Yes, this is where the meta layer gets very interesting. The research team ran an exercise using a highly specific constraint-based prompt, which they labeled V2A. They fed this prompt to 3 major large language models, GPT-5.4, Opus 4.6, and Gemini 3.1. Another community member also ran a similar prompt through Grok to expand the sample size.
Let me jump in here because the design of this prompt is the most critical part of the experiment. What makes a prompt constraint-based? The models were given the public performance specs, the 11C fast charge rates, the 268 watt-hours per kilogram energy density, the operating temperatures, and the suspected manufacturing constraints like screen printing and UV curing. But they were given absolutely zero material clues.
Not at all.
There was no mention of the titanium dioxide-coated carbon nanotubes found on Nordic Nano's website. There was no list of excluded materials from the Holyville patent. And crucially, lithium was already excluded by the prompt constraints based on Donut Labs' marketing saying not lithium.
That is a vital nuance, because the prompt explicitly told the models they couldn't use lithium. The models choosing sodium is not an independent discovery. It was the only logical alternative for a high-performance battery. We cannot present this as the AI magically guessing sodium out of thin air.
Right.
But what the AI models independently arrived at, the specific architectures they built around that forced sodium constraint, is what is so revealing. Because none of the models independently proposed titanium dioxide-coated carbon nanotubes without being prompted with that specific clue.
Exactly. In an earlier version of the prompt where that specific nanocoding clue was included, all the models seemingly converged on it. But this V2A stripped prompt strongly suggests that the previous AI convergence was just a prompt artifact.
The models were just echoing back the highly specific breadcrumbs they were subtly fed.
Yeah. When you take the breadcrumbs away and force them to rely on first principles materials science to meet the performance specs, they go in a different direction.
So what did they actually converge on when left to their own devices without the clues? All the models pointed toward a sodium carrier ion. They all leaned heavily toward hard carbon anodes. And they all proposed UV-curable polymer-based electrolytes mixed with ceramic fillers. The universal shift to hard carbon is significant. Hard carbon stores sodium ions via a mechanism called intercalation and pore filling. It's like sliding books into a rigid bookshelf. It is the safe, conservative choice. If you try to use a pure sodium metal anode, especially during an extreme 11C fast charge, the sodium ions pile up on the surface faster than they can smooth out, creating sharp dendrites, microscopic metal needles that pierce the separator and short out the cell. Hard carbon avoids the massive risks of metal plating. It's the physics-approved way to handle massive current.
Okay, so the AI models agree on the hard carbon anode and the sodium carrier ion. But while they agreed on the ends of the battery, we saw a massive split when it came to the middle, the electrolyte. And this split is exactly why tomorrow's cold test data is the most important piece of the puzzle. Tell me about the different electrolytes they proposed.
This is where it gets highly technical, but bear with me. Opus 4.6 suggests a composite of PEO NatHFSi polymer with a Nasicon ceramic filler. GPT 5.4 suggests a NaFSi-rich polymer with an NZSP ceramic.
Okay, alphabet soup, let's translate that for you. PEO is basically a widely used flexible plastic polymer. Nasicon and NZSP are solid, rock-hard ceramics that conduct sodium ions beautifully. So both Opus and GPT are suggesting a polymer-dominant composite mixing a flexible plastic sponge with hard conductive ceramic marbles to get the flexibility for screen printing and the conductivity for fast charging.
Exactly right. They are polymer-dominant composites. But Gemini 3.1 went rogue. It analyzed the constraints and suggested succinonitrile.
Succinonitrile. That sounds like something you'd find in a sci-fi novel. What is it?
It is a solid organic plastic crystal. It represents a completely different paradigm from a polymer matrix. Instead of relying on a flexible plastic sponge for ions to swim through, a plastic crystal maintains ionic conductivity through a phenomenon called rotational disorder.
Rotational disorder. How does a crystal, which by definition is a rigid structure, have disorder?
Imagine a perfectly structured crystal lattice, like a grid of molecules. But instead of being locked rigidly in place, the individual molecules stint and rotate in their fixed positions. It's like a grid of revolving doors. The sodium ions hop from one revolving door to the next to move through the material.
That is a phenomenal visual. Okay, so we have two models suggesting flexible polymer sponges and one model suggesting a grid of revolving crystal doors. Why does this fundamental disagreement matter for our analysis?
Because the physical properties of these materials react very differently to temperature drops. The polymer models Opus and GPT predict poor cold weather performance. They gave a low confidence rating to Donut Labs' claim of over 99% capacity retention at minus 30 degrees. As we discussed with the 2021 data, polymer matrices stiffen in the cold. The sponge freezes and ion mobility crashes.
But the plastic crystal model...
The plastic crystal model, Gemini, predicts excellent cold performance. It gave a high confidence rating to that specific marketing claim because that rotational disorder mechanism, those revolving doors, doesn't freeze up the same way a long polymer chain does when the temperature drops.
This brings us right back to the wager we made at the start of the deep dive and the impending cold test tomorrow. It is the ultimate discriminator. It is the most diagnostic data point Donut Lab could possibly release. We have our physical baseline from the 2021 CT coding report, only 54% retention at minus 20 degrees, and we have the current marketing claim, over 99% retention at minus 30 degrees. That gap isn't just an iterative improvement, it's a chasm that requires a fundamental architectural explanation.
It is genuinely falsifiable, which is rare in this industry. We have three distinct outcome scenarios for tomorrow's data drop. Let's walk through them. Scenario 1, the good outcome. The cell data shows greater than 90% capacity retention at minus 30 degrees Celsius.
If that happens, our polymer-dominant hypothesis, the flexible sponge idea, is severely weakened. Polymers just don't like the cold that much. The evidence would then strongly favor a high-ratio ceramic, a plastic crystal like Gemini suggested with succinonitrile, or a highly advanced composite model that somehow mitigates the polymer stiffening. The AI models like Opus and GPT that predicted poor cold performance would need to drastically revise their understanding of the material combinations.
Scenario 2, the bad outcome. The cell shows a 40 to 60% capacity loss. It struggles in the cold.
If we see that massive drop, it would be entirely consistent with the 2021 baseline. The polymer-dominant interpretation holds up perfectly. The physics behaves exactly as expected for a PEO-based system. But it would mean the marketing claim of 99% retention looks highly exaggerated, or perhaps it was measured under very specific, non-representative conditions, like preheating the cell internally before measuring.
And finally, scenario 3. The medium outcome. The cell retains between 75 and 90% capacity.
A medium result suggests substantial formulation improvement since 2021, but not a total paradigm shift. A polymer-ceramic composite model fits this best. The polymer allows for the manufacturing benefits of screen printing and flexibility, while the ceramic nanoparticles provide those crucial ionic highways that stay open even when the surrounding polymer starts to stiffen.
We have to reiterate a core tenet of our analysis here. This is not about proving anyone right or wrong for the sake of ego. We are saying, here is what the baseline physics of polymer electrolytes predicts. Let's see what the empirical data shows. And once again, we have to remind you, the people under the NDA know the real answer we're guessing from the outside. If they show 99% retention, there might be explanations or proprietary nanoscale mechanisms we simply haven't considered.
Okay, let's pivot from the chilling reality of the cold test to another claim that had everyone, including us, scratching our heads and questioning our sanity. Let's go back to that December 2024 SGS report. It showed the capacity of the cell actually increasing by 4.5% over 100 cycles. Critics immediately called it impossible. They called it fake data. They said batteries degrade, they don't grow capacity. But I want to push back on that skepticism. Is it actually impossible? Let's look at the academic case for this anti-degradation behavior.
It is a counterintuitive but fascinating phenomenon, often referred to in the literature as extended formation. And the peer-reviewed literature actually predicts exactly this behavior for the specific architecture deduced from the CT coding network. Now, a very important caveat must be stated here. Donut Lab has not publicly claimed they use screen printing or UV curing manufacturing methods. These methods are deduced from the corporate network investigation and the processes described in the Holy Volt patent. We are attributing this behavior to the hypothesized architecture.
Right. So assuming this hypothesized architecture, a screen-printed, UV-cured structure is correct, what does the academic literature actually say about capacity increasing? We have a paper from Gable et al., published in Scientific Reports in 2025. What did they find?
Gable's team looked specifically at screen-printed structured electrodes. At a microscopic level, a screen-printed electrode isn't perfectly flat. It looked more like a porous sponge. They found that capacity often increases during early cycling due to the gradual activation of secondary pore networks. Basically, as the battery cycles and physically expands and contracts slightly, the liquid or gel electrolyte slowly penetrates deeper into the printed sponge structure over time, unlocking active material deep inside the pores that wasn't participating in the chemical reactions during the first few cycles.
So it's not generating energy from nowhere. It's just finally accessing the energy that was hidden in the back of the closet. That makes sense. We also have a 2024 paper from the Journal of Energy Storage looking at UV-cured PEO networks. What happens to a UV-cured polymer when you cycle it repeatedly?
They found that these 3D cross-linked networks actually improve their ion transport pathways during early cycling. The mechanical stress of cycling, the slight swelling and contracting of the anode and cathode, helps the polymer matrix settle and conform better to the electrode surfaces, lowering interfacial resistance. Think of it like breaking in a stiff new pair of leather hiking boots. They fit better, flex better, and function more efficiently after you've walked 10 miles in them. The polymer matrix is breaking in.
I love that analogy. The battery is breaking in its boots. In another 2024 paper from ACS Applied Energy Materials looked at the ceramic fillers embedded in a polymer matrix. They found that under the mechanical stress of cycling, the ceramic nanoparticles gradually redistribute themselves, physically improving the continuous ionic highways through the cell. The marbles in the sponge shift around until they touch each other more efficiently, creating a better path for the sodium ions.
When you synthesize all of this independent literature, a clear picture emerges. No single paper suggests that this specific Donut Lab battery works exactly as claimed. But the academic consensus overwhelmingly points toward the idea that this extended formation behavior is consistent with our best interpretation of a screen-printed, UV-cured polymer ceramic composite. It moves the claim of anti-degradation from the realm of magic firmly into the realm of documented material science.
It's exactly what the literature predicts for this specific structural architecture. Now, to be clear, it doesn't mean the cell will last for 100,000 cycles and grow forever. Eventually, normal degradation will take over. But it does explain why the capacity went up over the first 100 cycles in the SGS test. It's just a cell that takes a very, very long time to finish its initial formation phase.
Precisely. The initial testing phase is just the warm-up act. And while we can debate AI chemistry models, PDF signatures, and peer-reviewed materials science papers all day, there's a physical reality check approaching that requires absolutely no deep scientific knowledge at all.
The paradigm gap. If this technology is real, if you can actually screen print a high-performance solid-state battery at room temperature for a fraction of the cost, why hasn't a titan of the industry, Toyota, Tesla, Panasonic, Samsung SDI, bought it outright? Why is a technology this potentially disruptive being licensed to relatively small, unknown companies like Donut Lab?
It is the most common and, frankly, the most valid skeptical question an analyst can ask. To understand why it hasn't been scooped up, we have to deeply understand the paradigm gap. Conventional battery gigafactories are marvels of extreme brute force engineering. They utilize massive high-temperature sintering ovens. They require colossal dry rooms that maintain near-zero humidity to prevent explosive reactions. And they require billions of dollars in capex just to pour the foundation. That is the incumbent paradigm. The CT coding platform, however, proposes ambient temperature processing, simple screen printing techniques borrowed from the textile and electronics industries, and a fraction of the deployment cost.
Paint that picture for the listener, because when you say dry room, people might just think of a dehumidifier in a basement.
A gigafactory dry room is a massive, highly controlled environment where workers often wear specialized suits, and the air is so dry it can cause physical discomfort. The energy required to maintain that environment is staggering. Now imagine walking into a review board of incumbent engineers who have spent their entire careers perfecting that extreme environment and pitching them a machine that looks like it prints t-shirts, operating in a standard warehouse at room temperature. To the incumbent mindset, this doesn't look like an innovative breakthrough. It looks like naivete. It fundamentally contradicts their foundational billion-dollar assumptions about what is required to manufacture a high-performance cell.
It's like trying to pitch the concept of a smartphone to a telegraphs company in 1910. They just can't map it to their physical reality. And let's be fair, it's not like CT Coding is a new startup with a fresh pitch.
Exactly. There is a 35-year trail of predecessor companies and iterative versions of this specific technology being almost ready for market. They have likely faced this massive due diligence wall repeatedly over the decades. Incumbents demand levels of prototype proof, complete teardowns, and full chemistry disclosures that a small IP holding company might be unable or completely unwilling to provide under standard NDAs. It forces them to bypass the titans and partner with smaller, more agile, perhaps more desperate entities willing to take the operational risk on the manufacturing platform.
Okay, so the incumbent giants aren't validating it. The review boards are skeptical. But there's a massive, heavy physical object that is about to validate it for us.
The Verge TS Pro motorcycle, which is slated to use this technology, is scheduled to ship to customers in April 2026.
Yes, the ultimate reality check. When those motorcycles ship and end up in customer driveways, the grand mystery of the energy density will be solved with nothing more than a simple tape measure and a digital weighing scale. The published specifications say the bike has a curb weight of 235 kilograms with a massive 20.2 kilowatt-hour battery pack. If you do the rough engineering math, subtracting the heavy HUD motor, the frame, the suspension components, and the rider interface, that leaves a budget of about 80 to 95 kilograms for the battery pack itself.
And here is the punchline to that engineering math. The bike does not need a revolutionary 400 watt-hour per kilogram battery to hit that physical weight target. The 268 watt-hours per kilogram that was measured in the December 2024 SGS report, the realistic nonviolent voltage number fits that standard pack weight budget perfectly. The 400 number floating around might be an aspirational target for future applications, like eVTOL aviation, but the 268 number is more than enough to make the motorcycle exist in the real world exactly as advertised.
So we have all these complex, disparate threads finally weaving together. The paradigm gap between skepticism and belief is narrowing. We have the 5-year testing trail demonstrating consistent non-standard behavior. We have the CTO clarifying the voltage window, which grounds the energy density numbers in reality. We have independent AI models converging on a sodium architecture that fits all the manufacturing constraints. And we have peer-reviewed literature backing up the strangest, most heavily criticized data point in the entire saga.
But the final puzzle piece, the one that could validate our entire analysis or force a massive, humbling revision of everything we've discussed today, arrives tomorrow with that VTT cold test data.
It really is the moment of truth. So we want to leave you with this final provocative thought to mull over while we all wait for the data to drop. If CT coding really did solve the battery manufacturing trilemma, if they really can screen print a high-performance solid-state battery at room temperature for a fraction of the capital cost of building a conventional multi-billion-dollar gigafactory, why didn't a giant like Toyota or Tesla buy the technology outright years ago? Perhaps the answer isn't that the technology is fake. Perhaps the answer is that massive legacy billion-dollar companies with decades of sunk costs in their own liquid lithium-ion R&D simply cannot absorb a sudden paradigm shift that comes from a tiny startup in Germany refusing to share its proprietary paste recipes. Sometimes the innovator's dilemma is the most powerful and stubborn force in the entire tech industry.
It is a profound question about how technological revolutions are actually adopted. They rarely come from the incumbents.
They usually come from the outsiders with sticky notes and coffee cups. Thank you for joining us on this incredibly deep exploration of the data. 5 years of proto testing, 3 labs, 6 independent chemistry models, and 1 cold test that could change everything. Tomorrow is the next anticipated donut lab revelation, the timer IS ticking.